welcome to the Deep Dive. Today, we're tackling something huge, the, frankly, explosive growth in power needed for AI, and how urgent this is becoming for our energy infrastructure.
Absolutely. We're digging into some fresh Wells Fargo equity research. This is from September 2025, and it really paints a stark picture. They've had to significantly revise their AI power forecasts upwards.
Right. So our mission today is to unpack the two big things driving this surge. First, just the sheer amount of cash the hyperscalers are pouring in, and second, something a bit more subtle, a shift in chip technology.
And then we need to look at how the grid is, or maybe isn't, planning to cope with all this demand.
Exactly. And here's the key stat to keep in mind. The forecast for U.S. AI power demand by 2030. It's a jump from 75 gigawatts to a, well, staggering 90 gigawatts.
Yeah, 90 GW. And that number isn't just pulled out of thin air. It's really anchored in that first driver you mentioned, capital expenditure, or Capex.
We're talking about the hyperscalers. Think Amazon, AWS, Google, Microsoft, Oracle, Meta.
Right. They're lined up to spend a record amount in forward-year Capex. The number is $437 billion.
$437 billion. And forward-year Capex, just so everyone's clear, that's the planned spending over the next 12 months.
And that figure, it's actually a 22% jump from what they were forecasting just last quarter. So the acceleration is real.
Okay, that's massive spending. But the second driver is where it gets counterintuitive, I think. It involves custom chips, ASICs.
Exactly. Application-specific integrated circuits. Things like Google's TPUs, Amazon's Trainium and Inferentia chips. These are becoming much more common.
Okay, hold on. This is the puzzle, right? These ASICs, they're generally more power efficient and they're cheaper. So why on earth does using them lead to more overall power consumption? That seems backwards.
It does seem backwards, but it boils down to economics and basically unconstrained demand for AI right now. The key is the cost per watt.
Yeah.
So estimates put these leading ASICs at around, say, $10 per watt. Compare that to the top-end NVIDIA GPUs, which might be closer to $40 per watt.
Wow, okay, 4 times cheaper per watt.
Right. And since AI demand is, for all practical purposes, unlimited at the moment, the real bottleneck is just Capex. How much hardware can these companies actually buy and deploy?
So if you have a fixed budget, that cheaper per watt cost means you can buy way more compute power, way more physical chips using ASICs than GPUs.
Precisely. You deploy maybe 4 times the hardware for the same budget. Even if each individual ASIC is a bit more efficient, the sheer volume of hardware you can now afford skyrockets.
So the total power draw goes up significantly.
Exactly. That efficiency gain gets completely swamped by the scale increase. Wells Fargo estimates this shift alone adds about 5 GW to the total power demand forecast.
Okay, so that gets us closer to that 90 GW figure,
Yeah.
which brings us smack into the infrastructure problem. If AI really demands 90 GW by 2030, can the grid even handle that? What are the physical limits?
Well, yeah, that's the critical question. And the main bottleneck isn't money, surprisingly. It's the actual supply chain for the big stuff, like heavy-duty gas turbines needed for utility-scale power plants.
Like building new power plants connected to the grid.
Right. The U.S. can probably only physically add about maybe 65 GW of new utility-scale capacity over the next 5 years, given manufacturing constraints and grid connection timelines.
So 90 GW of demand, but only 65 GW of new supply possible through the traditional grid route. That leaves a 25 GW shortfall.
A very significant shortfall.
So what happens if the grid can't keep up? Where does that extra power come from?
Well, the solution they're turning to is behind the meter, or BTM generation. Basically, building power generation right there on site at the data centers, bypassing the main grid.
Off-grid solutions, like what kind of tech are we talking about?
Mostly things like natural gas, simple cycle turbines, maybe some fuel cells. Simple cycle turbines are kind of like jet engines bolted to the ground. They're quick to deploy.
How quick?
You can get them up and running in maybe 1.5 years versus 5 years or more to get a big utility plant plan permitted, built, and connected to the grid.
Okay, so speed is the key.
Yeah.
But they're less efficient, right? That must cost more.
Is definitely more expensive to run. The estimate for simple cycle BTM power is around $132 per megawatt hour. Compare that to maybe $90 per MWH for efficient grid power from a combined cycle gas plant.
So quite a bit pricier. But I guess for these hyperscalers, the cost of having billions of dollars worth of GPUs sitting idle because there's no power, that cost is way higher.
That's the calculation they're making. Speed and certainty of power delivery outweigh the higher operating cost right now. Time to market is everything when you have that much capital tied up in AI hardware.
And this BTM solution, it relies heavily on one fuel source, doesn't it?
Overwhelmingly, yes, natural gas. The research projects that gas will fuel about 80% of this BTM build-out needed for AI data centers,
80%. Wow.
which translates to a huge increase in gas demand, specifically for data centers, potentially up to 11 billion cubic feet per day by 2030.
11 BCFD,
Mm.
just for AI. That's a massive new demand driver for natural gas.
It really is. They're essentially forced to build their own parallel, mostly gas-fired power system because the main grid just can't expand fast enough to meet this AI demand curve.
Okay, but building all this fast gas-fired capacity, isn't there a risk these BTM assets become, stranded in a few years? If solar and batteries get cheaper even faster, couldn't localized renewables become the better option later this decade?
That's absolutely the risk they're taking. It's a big bet on getting those GPUs earning revenue now, potentially locking in higher power costs and less flexible infrastructure for the medium term. It prioritizes today's urgency over tomorrow's potential efficiencies or environmental pressures.
So the bottom line seems to be AI's immediate need for power is just so intense, it's forcing decisions that prioritize speed above almost everything else, even cost and maybe long-term strategy.
Precisely. The urgency to deploy and generate revenue from AI is fundamentally reshaping energy infrastructure choices, pushing towards faster, localized, gas-heavy solutions.
And the source suggests this isn't slowing down. They project power, and gas demand keeps accelerating exponentially, even past 2030. Think about this. AI demand growth alone could soon match the entire current growth rate of U.S. gas production. We're just scratching the surface. So the question for you is, when speed is the ultimate driver, what other important factors inevitably get pushed aside?